Assalamualaikum warahmatullahi wabarakatuh and hi everyone. So today we're going to discuss one of the technique that we can use to analyze the performance of the system. That technique is root locus. So what is root locus? Root locus is a graphical representation of closed loop poles in the complex S plane as a system parameter variable. So this technique was introduced by Evans in 1948. So through this technique, we can evaluate the position of the roots, their locus of movement, and associated information. So from this all information, we can analyze the performance of the system. So what is the advantage of root locus? So first, root locus technique in control system is easy to implement as compared to other methods. So with the help of root locus, we can easily predict the performance of the whole system. That means from root locus that we draw or that we sketch, we can know the performance of the system in terms of transient and steady state. And also we can analyze the performance in terms of stability. Next, root locus provide the better way to indicate the parameter. To sketch the root locus, there are certain procedures that we can follow. In this lecture, the procedure that we will use is based on these 7 rules. So rules number 1, we have to identify the open loop and closed loop poles and zeros when k equal to 0 and k equal to infinity. So next, identify the number of root locus branch. Rule number 3, root locus should be symmetric about the real axis. Rule number 4, find the asymptote angle and also asymptote crossing point on the real axis. Rule number 5, crossing point at imaginary axis. Rule number 6, breakaway or break-in point on the real axis. And the last one, rule number 7, angle of departure or angle of arrival. Now let us go through rule number 1. So rule number 1 is identify the open loop and closed loop poles and zeros when k equal to 0 and k equal to infinity. So keep in mind, poles on the root locus is referred to the closed loop poles. So the location of these poles depends on the value of this k, which is varied from 0 to infinity. So when k is equal to 0, so the location of closed loop poles is equal to the location of open loop poles. So which is considered as a starting location of the root locus. Let us look at these two examples. So this example we have 2 poles and 2 zeros for the system. Referring to definition of a root locus, all the loci start from the pole when k equal to 0. So that means at this point k equal to 0. Okay. So when k varied, the location of this pole will change to other location. Okay. So this one will change, will move to here, and this one is here. And then when k is keep increase, so this pole will move until meet at this point and then separate. One pole will follow this route and another one will follow this route until meet these zeros. Until both pole will meet, one pole will meet these zeros and another one will meet these zeros. Okay. At this point, so the movement of pole will stop till k equal to infinity. Okay, let us look at the other example here. So this is the system without zeros. So what happened to the root locus? So when k is changed and start from 0 to infinity, okay, these zeros this pole will move from here to here, and also this one from here to here till meet at this point, and then break away. One pole will move to this direction, and another one will move to this direction, and k equal to infinity. Next, in rule number 2, we have to identify the number of root locus branch. So this can be done by using this formula, where number of branch is equal to the number of poles minus number of zeros. For example, if we have a system with 3 poles and 1 zeros, so the number of branch is equal to 2, because 3 minus 1. So if we have a system without zeros, for example, we have a system with three pole, so that means the number of branch is equal to 3, because number of zeros is 0. So by using this formula, so number of branch become 3 minus by 0. That's why the number of branch is equal to 0. For rule number 3, keep in mind that the root locus should be symmetric about the real axis. So this is because complex roots occur in conjugate pair. So this one we call symmetric, and this one we call asymmetric. So this is root locus, and this one is not root locus. Rule number 4. So here we have to calculate the asymptote of angle and also the asymptote of crossing point on the real axis. So in order to calculate asymptote of angle, we can use this formula where theta A is stand for asymptote. Theta asymptote equal to 2k plus 1. K here is a integer, start from 0 till infinity. And okay, 2k plus 1 times with pi divide by this one is refer to numbers of unit poles minus with numbers of unit zeros. Okay, this is how we can find the angle of asymptote. So in order to know the asymptote closing point, so we can use this formula where sigma a sigma asymptote equal to summation of unit poles minus summation of finite zeros divided by numbers of finite poles minus numbers of finite zeros. Okay, through these two equations, we can find the information about this angle of asymptote and asymptote closing point. Okay, for example, if we have this system with GS HS equal to K times S plus 0.5 divide by S times S plus 1 times S plus 2 times S plus 5. So from here, we can calculate the angle of asymptote by using this formula, where theta A, in this case, 2k plus 1. So k here is, we just put 0, 1, 2, 3, and so on. uh, and then times with this pi divide by number of pole. Number of pole here is we have fourth order system, because we have s power 4 here. If we multiply all together, so we get s the highest one is s power 4. So that means this one is number of pole is equal to 4. And numbers of zeros, by referring to this transfer function, so numbers of zeros is only 1, where the location of 0 is at s minus s equal to minus 0.5. So we just put the number of zeros here 1, and then we just substitute this value of k here. Okay, if k equal to 0, so we just put here, and then we get theta 1 is equal to pi over 3. So this one is equal to 60 degree. And then next we just put this second value of k, so we just put 1 here, and then we get theta 2 equal to pi. Okay, we convert into the degree, so we get 180 degree. And also theta 3 we get 300 here. Next, when we put this value of k equal to 4, so theta 4 become more than 360. So in this case, we can ignore that value, because where the value is more than 360, so it will repeat to the same angle as we calculate in theta 1, 2, and 3. Now we go to the rule number 5, which is cross point at imaginary axis. So what is cross point at the imaginary axis? Actually, this is the location where the closed loop poles are at when value of gain k changes at a certain value. So it is associated with value of range of gain k, which can cause the system to be in stable state. So to determine the crossing point, root average table can be used to obtain the gain value of this k when root locus cross at the imaginary axis. So after we get this value of k, the crossing point on imaginary axis can be produced by using the assisted equation from line s power of 2, so that we call auxiliary equations. Okay, so you can recall back what you have learned in control system fundamental on how to get this. This value actually is the value of k for the system before it become unstable. Rule number 6, breakaway or break-in point. So the breakaway or break-in point is the starting point when root locus start to leave or enter the real axis. So that means this breakaway or break-in point only occurs on the real axis. So this is the formula that we use to obtain the coordinate for this breakaway or break-in point. So for example, we have a system with gs equal to k divided by s times s plus 1 times s plus 2. So from this system, so in order to find this breakaway or break-in point, so first we have to find the characteristic equation. So this is the formula for characteristic equation 1 plus k gs hs. So we just substitute all these gs into this equation, and locus is considered as a system with unity feedback. So hs is equal to 1. The characteristic equation become 1 plus k divided by s times s plus 1 times s plus 2, all this times 1 equal to 0. So from here, so we rearrange this equation become s times s plus 1 times s plus 2 plus k. So from here, k is equal to negative s cubed minus 3s squared minus 2s. Okay, after we get this value of k, so we just use this formula and we differentiate this k. So dk over ds equal, we differentiate this k equal to 0. So dk over ds equal to 0. So we just put k, this equation here, and then by solve this differential equation, so we get negative 3s squared minus 6s minus 2 equal to 0. So from here, we factorize this equation, so we get s1 equal to negative 1.577 and s2 is equal to negative 0.423. One of these s represent breakaway or break-in point, depends on the location of pole and zeros. So come back to this GS. So from this system, so we know that the system consists of 3 pole and without zeros. So the location of pole is at 0, -1, and -2. From this location of poles, the breakaway point will occur between these 2 poles close to the j omega axis. So in this case, the value of the breakaway point is occurs at negative 0.423. Okay, based on this information, so the system only have breakaway point because there is only poles involved in this system. Okay, next we go to the rules number 7 about the angle of departure or angle of arrival. So this angle should be considered for a system that has open loop poles or open loop zeros or both, which are located at the complex path. And that means when we have poles or zeros at the complex path, we have to find this rule number 7. Okay, for feedback system, this rule refers to the angle that has to be obtained as the root locus begin to leave the original position when k change. This angle is known as angle of departure. Meanwhile, for the system that have zeros at the complex path, then the angle obtained is known as angle arrival. So angle of arrival is an angle whereby the root locus start closing to 0. Let us look at this example. So in this example, we have a system with 4 pole and 1 zeros. In this case, we have pole at the complex path and zeros only on the real axis. So that means in this case, we have only angle of departure. So how to calculate angle of departure? So to calculate angle of departure, we can use this formula where summation of angle for zeros minus summation of angle for pole equal to 180. This one actually plus minus 180 degree. So angle in this case is angle from this horizontal or from this real axis to this line. For example, in this case, we have two poles located at complex parts. So we just take one of this pole as a reference. In this example, we take this one as a reference. So all pole on in this S plane, we refer to this angle, this pole. So for example, pole at s equal to 0, this one we refer to this pole. Also same pole at this place, we refer to this pole, and also for these zeros also refer to this pole, and this one also refer to this pole. So that means this is reference. Okay? So we have to decide one reference among these pole or zeros that are located on the complex path. So from here we can calculate the value of theta here. So this one we call theta 1. And next, this one, for the parallel line with this real axis. So this angle automatically is 90 degree. So this one, we have to use theorem Pythagoras to calculate this theta. So this one is theta for pole, and this one is also theta for pole, and this one is also theta for pole. So in this case, there are 4 pole, including this reference pole. So now this pole, this angle, we can calculate through theorem Pythagoras. But this one we have to calculate from this equation. Okay, from here we can get the angle of departure. That means angle for this pole. Okay, for zeros, only one zeros here, so that means we just use theorem Pythagoras to get this theta, and then we put all this into this equation, and like this. In this case, this value can be calculated from here through theorem Pythagoras. This one also can be calculated through theorem Pythagoras. Okay, this theta 2 also can be calculated. Theta 2 is here, can be just put 90 degree, and this one is theta P3. Theta P3 is referred to this one. Okay, this is theta P3 is theta that we have to calculate using this formula, and this theta P3 is the angle of departure. If the system have zeros on the complex part, and the procedure to find the angle of arrival is also same like techniques used to determine angle of departure. That's all for today. Please do exercise that I already upload in you learn, and see you next lecture. Assalamualaikum warahmatullahi wabarakatuh.